Okay, welcome back. Hope you had a great break. Our exam is tomorrow and Thursday. Exam number 2. Most of the exam is Module 4, exponential functions. I hope that all didn't fall out of your brain over break. We worked hard at understanding exactly what exponential functions are, not just how to plug values in, right? So all that stuff will be tested on the exam. So hopefully you've started studying by now. If you've not started studying, you got to make sure you get all those basics about exponential functions because those are tested. Don't forget about this tutor center, Pathways Tutor Center, open to help you study. ECA 202, Monday through Thursday, 7:30 to 6. 7:30 to 6. Okay, if you go to exam prep, you see that I posted, and this was, I think I sent you an email at the beginning of break, right? Telling you that this is up. So you got your outline. You won't see that. And then this is an archive of exponential quizzes from past semesters. Okay, so if you're interested in more practice on exponential stuff, things that I put on quizzes in the past were the things I considered the most important. So lots of good material there. Okay, and then of course this is comprehensive. So everything on the exam is talked about somewhere here on this. Okay, so make sure you understand it all and can apply it to problems. All right, and then for Thursday you have an assignment, all of which is material for, so that first thing, for Thursday, March 20th. It's a web work shorter than average, and then 3 written homework problems. Okay, so this stuff is all covered on the exam. Please make note of on 66 and 67. If you want the full benefit of doing those problems, you won't use your graphing calculator. Okay, and then change part B based on what we do today. You'll see. Okay, so in part B, you just change the wording there to what I have. It's the same idea, though. Okay, questions about this week? The exam, same procedure. You can go tomorrow or Thursday. You can go in as early as 10:30. You need to be in the door by 6:30, and then you can work until 8. Okay, so as long as you want to take the exam. Questions about any of that? Again, don't forget the tutoring center. And then my office hours, Thursday, I have normal office hours. You can check when, do you have time coming up soon in the tutor center? Tomorrow from 8:30 to 10, she's in the tutor center. And then I have my office hours, like I said, Thursday, 11:30 to 1 before class. Okay, any questions about what's going on this week? Okay, so all that stuff that we did at the beginning of the exponential module 4, we did like a month ago. So you got to really make, and that initial stuff was all the basics that we built upon throughout that module. So make sure you know your stuff. Study, you got to go back and study, and then find one of us to have conversations with about your questions. All right, so I think you have homework you're turning in. So as you're turning in the homework, I'm going to give you a practice problem here. Here it is. What I want you to do is, let's that's not what I want. Oh, does it just shut down? Just shut down on me. All right. Okay. So, Hunt. Okay, here's the problem. we go. Okay, so here's this problem. I went to this polynomial. So what have we talked about so far with polynomials? So we're looking at different aspects, ways to analyze them, and create their graphs. So in a problem like this, you don't use your graphing calculator, okay? So we're not going to use our graphing calculator because we want to know the mathematics behind what creates the graph, and that's what you're expected to know. So what were the different aspects to polynomials was one of the things that we talked about in terms of analyzing a polynomial. What was one of the things? Full house today. So this is how class should be. Every Tuesday and Thursday, you should all come. All right? I take attendance, and so pretty soon, if you're already over the limit for attendance misses, which is 4, and many of you are, you're going to get 1 more the rest of the semester. And then after that, E in the course, okay? So come to class every Tuesday and Thursday. Yeah?
You look at zeros or the roots.
Zeros or roots, okay? What else?
Degree.
Okay, what about this? So what does the degree help you with? What is it? End behavior. End behavior, right? And there was one more thing we've talked about so far.
Leading term.
That's end behavior, right? Leading term gets us the end behavior. So that's end behavior. What intercept? Y-intercept. What about x-intercepts? Those are okay. So that's the graph, the visual version of the zeros or the roots are the x-intercepts.
You do that by factorizing, right? You want to find the x-intercept. If you factorize the equation, then you easily find the x-intercept.
Okay, so yes. So I'm going to set you loose here. Just work on these 3 things for this polynomial h of x. No graphing calculator for this, okay? So you're going to, this is hopefully review. This is review. Determine these 3 things for this polynomial h of x. Coming back. Hold on. Quick, write it down before it goes away again. Oh, we're good. Okay, compare what you got so far with the person next to you.
You mean what if we just wanted to have this?
Okay, let's see who did their homework. So, y-intercept. Jared. Oh, sorry. Well, you can do the y-intercept you want. I was going to do end behavior, but whatever you want. End behavior. But how do you know? Tell me the process. Leading term. Okay, so we're going to get the leading term, which is? Process. Tell me. Multiply what? The whole thing? Okay, so what? X squared.
After you distribute multiply the squared, parentheses,
X squared.
and 3x, which gives you 3x to the 6th.
Okay, so to get every single term, so this polynomial has several terms, like a bunch. To get a term, you would go through and you'd pick one from each factor. You pick one from each factor. So if we want the leading term, which are we going to pick? The biggest x from each. So once we pick the biggest x from each one and multiply those, that'll give us the leading term. Okay? So 3x to the 6th. So that means that as, keep going, you're doing good.
As x approaches infinity,
Okay?
y approaches.
So as x gets large positive, he's saying y also will get large positive. Agree? We're just looking at that. All right? So I'll do that in red. So that means over here, what's going to happen to the graph as we go to the right? Go up. Right? So it's going to go up over here as x gets very big positive. Okay? Keep going. Really big negative. Negative. Y will get really big negative. Agree with that? Some nodding, some shaking. So you take a big negative value and take it to the 6th. What do you get? Positive or negative? To the 6th. Positive. And then multiply it by positive 3. You get? Positive. You got to go through the math. Go through the math. You're going to put a big negative number in there. If you raise it an even number to an even power, it becomes positive. Multiply it by positive 3. You get positive. So when we go to the left, what will the graph do? Go up. So the red, I'm showing the end behavior in red there, based on our leading term 3x to the 6th. That should be reviewed from your homework. Okay, let's do y-intercept next. Buddha, tell me about the y-intercept. Why? What's true about the y-intercept? So how do we find it? What's true about that? What's true about every point on the y-axis? Yeah, Alex?
X equals 0.
Yeah, so x equals 0. That's what the y-intercept means. It's going to be the point where x equals 0. So we apply that to the formula. So Alex, how do we get it?
So we're trying to substitute all the x's with 0.
Yeah, so it's h of 0. H of 0 is the y-intercept, right? H of 0 is the y value when x is 0. In this case, it is? You're all thinking it? 0. Okay, 0. Okay, so we got the y-intercept right there. It was in red. Right. So our actual conclusions about the graph, I'm putting in red. Okay. All right. So last is zeros roots. So we haven't done this specifically in class, but I think you watched a video about it. And so the factored form is very convenient for finding the zeros of the roots. Why? Because it's a bunch of things multiplied together. To get something to be 0, all you need is one of them to be 0, right? So we can look at each factor and just say what value of x will make this thing 0. So let's write down the factors down here. What's the first factor that we're looking at?
X squared.
Okay, so and then actually it's the factor itself is just x, okay? And so what is the corresponding root to x? 0. Well, so that we already got that, right? So that was our y-intercept. So here the y-intercept, when it's 0, that's also a root, okay? Next factor, x plus 3. What's the corresponding 0 or root? Christian wants -3. Agree with that? Yeah, so what are roots? Values of x that make the function 0. So what value of x here will give us a 0? -3. Next factor. 3x minus 4. Corresponding root. 4/3. Last one. X plus 1. Corresponding root. -1. All right, so we've got roots or x-intercepts at all these values. 0, -3, 4/3, -1. So that's all we've talked about so far. You may have learned other things in the past or you read, but that's all we've got so far. And so basically, since there's no more roots to the left of -3, how's the graph going to leave -3? What's it going to do as x gets more negative? It's going to do this, right? We know the end behavior. There's no more roots, so it's got to it's going to head to -infinity from here. Okay, what about 4/3? Sorry. It's going to go positive infinity. Same with this, 4/3. Graph will go up from there. But in terms of what's happening in between, we really haven't discussed that yet. So let's just see if we've got this much right. So I'm going to turn it on. I'll turn it on in red to match. We do, except that I don't know where 4/3 is. Okay? So I was perfect. Except this is 4/3 right here. Okay. So now the question is, we want to know beyond just the roots and the y-intercept and the end behavior, what's called middle behavior, or what's happening at the roots. So we could make this sketch if we needed to. So here's what we're going to look at. Take a look at here at -3. What do you notice close to -3? This. Well, so yeah, doesn't it look like a parabola? Doesn't it look like what you've seen in the past as a quadratic function, x squared? Okay, and even if I zoom in there, and don't look at anything else, you can see that looks somewhat like a parabola right there at -3. So what is it in the, I'm making a mess here. So what is it in the, wow, I moved it. There we go. What is it in the formula that might indicate there that at the root of -3, we have something that's like quadratic? Can you see it?
8x plus 3 to the power 2.
So is that consistent with this shape of a parabola? Something squared? Yeah, so when the factor is squared, we see that we have something of a parabolic shape. So what about at x squared, or at 0? Is it consistent? We're seeing the same thing. Now, this one's bent down. It's opening downward. That's fine. This one's opening upward. But it's just the overall, what's happening there is that the graph comes and hits that root and then stays on the same side, creating a parabolic shape. And the formula is consistent with that in that the corresponding factor is squared, whether it's at x plus 3 squared or x squared. Omar.
I have a question.
Yeah.
The x plus 3 to the power 2.
Okay.
In the graph, it doesn't actually intersect. That just touches the line. Would that be included? Would that be included as an intersect? If it just touches the line, it doesn't cross.
If you plug -3 into h, what do you get?
You get plug 0. Yeah.
You get 0.
Yeah. I mean, I understand that, but then over here it just touches the line. It doesn't intersect. Would that be included as
Doesn't
an
intersect. I don't understand. It doesn't intersect.
It doesn't intersect. So it's just
If you plug -3 into the function, what do you get?
0.
Does it intersect the x-axis?
No. Wait.
It doesn't go
It
through.
doesn't go through. But
That's
it doesn't-
different than intersecting.
Oh,
It doesn't go through. It does exactly what a parabola, like the parabola x squared does. It comes in, touches at the lowest point is at 0, y equals 0, and then it goes back up.
okay.
Does that answer it?
Yeah, so it doesn't intersect. But it doesn't cross.
It doesn't cross through.
Okay.
It has quadratic behavior, like a parabola. Okay, so then what about at -1? What's happening at -1?
Go straight through.
It goes straight through. So if I were to zoom in on that, what would we see? So there he goes, right there. So there I am. I've zoomed in at -1. What do you see? Okay, so what in the formula is consistent with that? It agrees with that. Nadine. What about the x plus 1? So x plus 1 is getting us that root at -1, but what about the fact that it goes straight through? Linear. So where do we see that here? That's what I'm saying. Where do we see that linearity in the actual formula for the function? Okay? Yeah.
It's in the degree.
Okay.
First degree, so it doesn't curve.
Right. So isn't this like x plus 1 to the first? Right. So that's like a linear function, and there it is. It's like a line going straight through at that root of -1. Okay, so that should be the same thing that's happening then at 4/3. At 4/3, it should go straight through. Let's take a look. Let's see if this works. Okay, did I no? Again. There we go. So at 4/3, what's happening? Does it agree with what we see in the formula? 3x minus at 4/3. What's our power on our factor? 1. And it goes through, like if we were to zoom in on that, we would see a straight line. Okay, so what we're talking about now is the behavior at the roots. Okay, so not just the points themselves, but the behavior at the roots, which is determined by what we call the multiplicities on the factors. So when we're analyzing these, we want to make this chart that includes factors, roots, and their multiplicities. So for the factor x, what's the multiplicity on the factor x? It's a number, right? So it's a number. In other words, what's the power on the factor x? 2, right? And what do we see? We see that quadratic shape, parabola shape. Okay, x plus 3. What's the multiplicity on the factor x plus 3? Also 2. Again, we saw this parabolic shape at -3. 3x minus 4. Multiplicity. 1, x plus 1. Both of those go straight through like a line. Okay, so this is what we call, this is determining the middle behavior. So we talked about end behavior. So now the roots and their multiplicities and the y-intercept are what we call the middle behavior of the graph. So relatively close to x equals 0. As opposed to end behavior where we look at large x positive and large x negative. Yeah? Sure.
How did you determine the highest one?
For like this, we haven't. So we haven't talked at all about these what we call local max and mins. Okay? So we're not finding those. Yeah, we're not going to take the time to talk about what we call local max and mins. So just the 4 things. Okay? Zeros, end behavior, the y-intercept, and then the root zero behavior or root behavior, which we get from the multiplicities. So those are the 4 things we want to know really well. Okay, any questions on this new thing, multiplicities and root behavior? So here I'm going to change it up. I'm going to give you the graph, and you need to construct the function formula for it. Okay, no graphing calculators, so don't use it. Got to know your stuff. Okay, can I erase? Here it is. So all those tick marks are 1. Okay, so this is 1, 2, 3, 1, 2, 3. Okay, so see if now you can use what you've learned, be a little ingenious here, and put together a formula for this without your graphic, without your calculator. So using what we just learned, but kind of working backwards. Everyone's writing, working on this. You can't, just don't sit there and stare at the screen, okay? Think of it as studying for the exam. Exam is in a day or 2. So kids, make the table that we made in the lower left part of the screen. Make that table. Okay, show me what you got. What about multiplicities, though? Multiplicities, we're going to change that. Multiplicities matter. Okay, so those factors and multiplicities.
But when you plug in,
How could you alter
you plug in one,
different functions to keep that stuff intact?
so when you multiply out,
Then you're going to use one yourself to determine your minus that. You can just do it all in factor form if you want. Okay. How many roots do we have? Tim, tell me the roots. Negative 3, 0, and 1. What do you think? Just negative 3 and 1. Yeah, so you don't. So it's just roots are x-intercepts, right? We're across the x-axis. Okay, so what's the factor associated with negative 3? Ahmed. What is the factor associated with a root of negative 3? No, the factor would be like x plus something or x minus something. So we're really asking what expression, if we plugged negative 3 into it, would give us 0? What expression, if we plugged negative 3 into it, would give us 0? Why? Because negative 3 is a 0. All right, what about the factor for 1? Yeah? X minus 1. Okay, what's the multiplicity? Now we have to look at the graph. What's the multiplicity at x plus 3? Just go straight through, right? So it's like a line. Or linear to the first power. What about x minus 1? 2. So we can make kind of a first attempt. If we call this f of x, we can make kind of a first attempt at this. And we're going to do what? X plus 3 to the what? To the 1. And then x minus 1 squared. So that has our roots at negative 3 and 1 and has the right behavior. Negative 3 goes straight through. We raise that to the first. And 1 is parabolic shape, so it's squared. So now, is that the only function that has those characteristics? So how can we write all functions that have those factors and multiplicities? How can we describe all functions that have those factors and multiplicities? Because there's more than one. There's actually many. Really, we could multiply those two factors by any real number called a. And it still preserves these factors and multiplicities. Does that make sense? So it could be negative 2 times these two things. It could be 8 times these. It could be 100 times those. And it still has the right multiplicities and factors. It has the right root behavior and roots. So how do we figure out which one we want? How do we find that a value? What's going to help us get it? Somebody new. Christina, any ideas? What have we not considered yet? Yeah, the y-intercept. So what function statement can we make with the y-intercept? What has to be true regarding f? F of what has to be what? F to 0 would have to be -1. So we need to find the a value such that if we put 0, f of 0, we're going to get -1. All right, so f of 0 has to be -1, and it has to be a times, well, it's f of 0, so what are we going to do over here? 0. So we're going to get 3 and -1 squared. So we're evaluating our first attempt here, or basically any function that matches our roots and root behavior with x equals 0 in there, and we ought to get -1. So what a value does it? So -1 has to equal a times 3. So the a value that will give us the right y-intercept is -1/3. So now we can write, now we know exactly what f of x is. F of x equals -1/3, x plus 3, x minus 1 squared.
The same thing if I have -x minus 3, and then 1/3 positive.
What now?
If my root for 3 is -x minus 3, and then I have 1/3 is
-x minus 3 and positive 1/3? Yeah, that works. Okay, did you see what happened? Does it make sense? What we just did there. So just the factors in the multiplicities gives us a whole family of polynomials that have those roots and those the behavior at the roots. Okay, but we need to get this specific polynomial, and so we can get that by looking at our y-intercept and getting this coefficient that makes the y-intercept right. That when we plug 0 in, it gives us -1. And in this case, that coefficient was -1/3. All right, another practice problem. Can I erase what's out there? Okay. Here you go. So while you're working on it, I'm going to take attendance.
that pointer relevant?
Start with your table. All right, show me what you got. So there's a little different this time. Is there something there? Oh, nope, it's not right. So it's just, that's just what we call a local minimum. But we haven't really done any analysis at all. That's what polynomials do, they have like local maxes in them. We haven't really gotten into like what that value is.
just focusing on the middle behavior. We're just focusing on the roots of behavior at the roots and the y-intercept. Much progress. Good. Okay. No, it's not that A is 0, it's that's showing you that A can be anything. Because your y-intercept is already a root. You can use it to find A. That's not showing you. 0 equals A, so 0 means A can be anything. Yeah. Negative 2. Remember that you got the right idea. Yeah, I don't remember if that's the right answer, but you're doing right.
Okay, tell me the roots. Alec, what are the roots for this one? Negative 1. 0. 2. And how about the corresponding factors? You're on a roll. X plus 1. X. Very good. All right. Aaron, take over. Multiplicities at x plus 1. What's your multiplicity? At x. 2 and x minus 2. 1. So let's give an initial formula here. Can you write? We'll call it this one G.
Alright, so x squared
X squared
times x plus 1
times x plus 1
times x minus 2.
x minus 2. Is that what this is? Is that the final answer? No, so what else do we need in that formula? We're going to start off by representing every function that has these factors and multiplicities. So there's not just one, right? There's lots. And so how do we represent lots of functions that have those factors and multiplicities? Yeah, we need some any real number. A for any real number. Now we've got them all. But we want this one that graphs just like this. So what about using the y-intercept? Doesn't work because this gives you 0, and at 0 it's 0, so basically you get 0 equals A times 0. That doesn't narrow down the possibilities. A still could be anything. A still could be anything for that to be true. So when your y-intercept is actually a root, this doesn't work anymore. So we need something else to get A. G of what? G of 1 equals negative 4. So that equals A times, what am I going to plug in for x? 1, not 0. So because we know when we plug x in for 1, or 1 in for x, we ought to get negative 4 for y. So this would be times 2 times negative 1, is that right? So negative 4 equals A times negative 2. Therefore, A equals positive 2. Did we do the math right? So therefore, g of x is 2x squared, x plus 1, x minus 2 squared. Let's see. Let's see how smart you are. Did I write it wrong? And that's it. That's what I originally graphed. 2x squared, x plus 1, x minus 2. Okay, one more. Okay, so this hits a high point kind of off the top of the screen, but that doesn't mean we're not considering those. So just know that goes up and hits a high point and comes back down. Okay, this also has something different, something new for you to discover. Oh, now we're running on emergency battery power. I plugged it in, but I didn't attach it to the computer. Okay, show me what you got.
Okay. Want me to check what you got, or your questions? Okay, so is it actually stuck in terms of multiplicity? So we've been looking at like what does it behave like? So is that like linear? Actually, it doesn't. Like linear would be like straight through. So it's like doing so what behavior is that?
Well, yeah, if you have the point negative one, so spit out this one. So then we know that whatever coefficient goes here is like that. And just put the variable there, and then plug negative one into that. And then you'll have all numbers with one variable.
Oh,
So see, this should have been.
It's like that's what you picked up on it.
If this is negative one,
oh,
then it will
thank you.
multiply by that. You get that.
Okay, so what's the factor for -2, Jonathan? If the root is -2, what factor do we get? X plus 2. Keep going. How about for 0? The factor. But not the multiplicity, just the factor. X. And what about for 3? All right, what's the multiplicity at -2? Patrick?
At -2, it should be 1.
And then what about at 0?
At 0, it should be, I said 3.
And why did you say that?
Because a square involving something to the second power is a parabola.
Okay.
When you do something to the third power, it does exactly that. It goes down.
Right, so if you recognize that behavior, so we're talking about root behavior, and so this behavior is like cubic behavior. Y equals x cubed looks just like that. So it goes through like a multiplicity of 1 would, but it kind of hovers there, and then it doesn't go straight through. It kind of hugs on the axis, and then goes through. All right, and then multiplicity of 3, 1. So maybe we'll call this P of x. Initial guess would be A times x plus 2 to the
1, x times x to the 3, and x minus 3 to the first. And then how are we going to find this specific value of a? So, Austin, how are we going to get this specific polynomial, or in other words, what is that value of a?
You're going to set that equal to 1, and then
Set what equal to 1?
a times plus 2.
Oh, the whole thing?
Yeah, set the whole thing equal to -1.
-1. When x is what?
Negative.
-1. And when you do the math, a comes out to be 4.
Negative one.
I'm hearing -1/4.
Oh, the whole thing. Yeah.
Yeah. So yeah. What do you get?
Negative.
Is that right? Here we go. Check it out. There it is. Okay, questions on these types of problems? Given the graph, come up with the factored form. Okay, so let's go back, and now we'll put it all together. I wanted to, what about the end behavior with these types of problems? Well, end behavior it's just a way you can check. So we can take the end behavior on this and just verify that it is, if we had come up with this answer, we could just check to make sure the end behavior is right. So what do we look at to look at the end behavior? Okay, leading term. So, Brooke, what's the leading term for this? Could you come up with the leading term? -1/4. X cubed. Is that it? We're gonna times x times, and that gives us fifth. Okay? So as x gets really large positive, what will that do? As x gets really large positive. Would it be negative or positive? Negative, because x to the fifth will be positive, but we multiply by a negative. Does it agree? Yep. So our end behavior to the right, y is decreasing, very large negative. Okay, what about when x becomes very large negative? What does y do? So what about x to the fifth? Positive or negative? Negative times -1/4. Positive. So that means as we go way out to the left, graph should go up. And it does. It does. So with these problems where you're given the graph and then you're coming up with the formula, you can, at the end, once you have your attempted answer, then you can do it as a check of it. You can find the end behavior and see if it matches what you were given with the graph. Okay, cool. So again, no graphing calculators. Where's this last one? This one. Put it all together, and without your graphing calculator, see if you can make a good sketch of this graph. So, let's list our 4 things. And this is that kind of the order you have to approach this as. Okay, end behavior. Y-intercept. Zeros or x-intercepts. Root behavior. And as you're making a sketch, that's kind of the order that you you go. You get the ends, and you're going to use that root behavior and kind of work your way in and create the graph from outside in. Okay? See how you do. If you want the full benefit here, don't graph this on your calculator. You can use your calculator to make numeric things if you want that. That's fine. Computation. Don't graph. Okay, questions? Show me what you got. Okay, let's see how we did. How about end behavior? How about Shola? Did you get the end behavior? So tell me process, not just answer. Leading term? What did you get for the leading term? Negative 4 over 30, x to the 6th. You guys agree? We got x cubed, and x, and 4x squared, and negative 130. Agree? think you got it. All right, so as you're saying, as x goes over here? He says decreasing both sides.
Yeah.
If his leading term is right, then that's right. 3, 4, 5, 6. There's just 6 of them. Okay, so you're saying out to the right, up or down? Down. Out to the left, down. Okay, so I'm gonna just put arrows like this. Okay, end behavior. So y-intercept. Taz, did you get the y-intercept?
Y-intercept.
Yep.
I got a really big number.
Yep.
Y was 6. Yeah, 627.
627 point something, right? 627.2. Okay, there it is. Okay, how about the zeros? Let's see. Justin. Let's make our table.
Negative 4. 6. 7 over 2.
Negative 4, 6, 7 over 2. What do you guys think? What's the multiplicity on our negative 4? 3, and then 1 and 2. Okay, so let's plot those points first of all. 0 at negative 4, 0 at 6, and 7 halves, 3.5. So here's where we've got everything but the middle, what the middle of this graph looks like. So we have to kind of work our way in from the outside and follow the multiplicities. So the first thing is this thing is going down over here, so it's going to come from that root, right? Will it go straight through, or parabola, or cubic behavior? Parabola?
Yeah.
No, this is our 6.
No, 6.
Straight through.
I can go.
Goes straight through, okay? And then what happens at 3/5 or 3.5? Parabola. So it's gonna hit some high point here, but then it's gonna come down and be like a parabola there. And then it'll go through our y-intercept, which may or may not be the maximum. I'll just make it the max. But the maximum could be over here, or it could be over here. That doesn't necessarily have to be the high point. Okay? That doesn't necessarily have to. We don't know. All we know is it goes through that point. And what about negative 4? Cubic, so like this. So here's a possible sketch. We don't know where there's somewhere there's a maximum here, we don't know. Somewhere there's a maximum here, we don't know for sure. But we haven't, figured that out. So let's take a look. I'll make it red so it stands out. Okay, so everything that we did, we got right. So we missed the height of this, which we did analyze. Okay, any questions on that example? Yeah.
What did you do with the -1 over 30? What's that inclusion?
It just it comes into our finding the y-intercept and finding the leading term.
Oh, okay.
So in the y-intercept, you're plugging in x equals 0, it'll come into that. And then in the leading term, it came into the leading term. Yep. Other questions? Okay, so then I have some questions for you about this graph. We already did all that. So there's 5 intervals. Here from -infinity to 4. So I'm going to make black lines to mark off the intervals. From -4 to -1.5, or just about there. From -1.5 to 0, or just over 0, so somewhere around there. And then from 0 to 1.6. and then from 1.6 to 3.5. So we'll just call those A, those intervals A, B, C, D, and E. So for each of those, you're going to answer these three questions. This is review from stuff before, right before we did these polynomials. So the reason we did polynomials when we did is they follow this covariational reasoning. They have these, their behavior is such that we ask about these questions about y increasing and decreasing, changes in y increasing and decreasing, and then the rate of change. So remember when we did all that stuff, like with the bottles and me walking. Remember I was walking in here? Remember that? Okay, so those are the 5 regions. So this is definitely a verbal exercise. You're going to get a partner. For each of those 5 intervals, you answer these 3 questions. Is the value of y increasing, decreasing, or staying the same? Are changes in y increasing, decreasing, or staying the same? Is the rate of change increasing, decreasing, staying the same? Go. Review for the exam. Review. Everyone get a partner. There should be 18 conversations going on.
I mean, I know what you mean. You just go with the very slowly first.
Oh, let's see.
So like, what we did was
the range where it's decreasing high at you. It's increasing at you start from here to a small and each time it gets bigger. So this between and C gets the biggest, then side decreasing the change side. So the y value increases.
All right, we'll start right with B, just for time's sake. So in B, is y increasing, decreasing, or staying the same? Y is increasing, right? Values of y are getting greater. What about the changes in y? Increasing or decreasing? Those changes in y. They're increasing. They're positive changes, and they're getting more positive. Increasing changes, okay, in B. So what about the rate of change? The changes are increasing, then the rate of change is increasing. So the rate of change, not only is y increasing, but the rate of change of y is increasing. And that makes this concave up shape, right? Okay, in C, is y increasing or decreasing? Increasing. Changes? Decreasing. So the rate of change? Decreasing. Concave down, right? Concave down means the rate of change is decreasing. So y is increasing, but it's increasing at a slower rate as x increases. All right, this, in D, changes are, so y is decreasing, so the changes are positive or negative? Are they getting more or less negative? All right, so are these changes increasing or decreasing? Did you learn something? So those lines get longer, but those are representing negative changes. This is decreasing changes. Therefore, the rate of change is decreasing in D. Negative changes that are becoming more negative are decreasing changes. Therefore, our rate of change is decreasing. Finally, in E, changes are negative or positive? Negative changes getting less or more negative? Less negative, which means those changes are increasing. Negative and getting less negative is increasing. And so that corresponds with the concavity. Where it's concave down, your rate of change is decreasing. Where it's concave up, your rate of change is increasing. Okay, if you got homework for Thursday, there's a little written, and there's web work. It all pertains to the test. And you can take it Wednesday or Thursday. Get your questions answered. Study.